Have you ever clicked a simple menu button to like slide out a sidebar, only to watch your beautiful data chart just awkwardly bleed right off the edge of the screen?
So yeah, we've all been there. It's the worst.
It really is. And today we're doing a deep dive into an article by Aaron Rose. It's titled "The Secret Life of JavaScript: The Resize." It was published on the tech-reader blog.
Right, and it's a great piece.
Yeah, so our mission for this deep dive is to basically figure out exactly why modern web layouts break in this very specific way and, how to fix them using a fascinating piece of browser technology. We've got the article, some of our own architectural notes, and a prime example of a developer really pushing the limits of modern UI.
I love this topic because, well, the source material doesn't just give you a dry technical manual. Rose grounds the whole problem in a super relatable scenario.
Yeah, exactly.
You've got this developer, let's call him Timothy, right?
Mhm.
And he builds this highly customized canvas chart for a complex analytics dashboard.
And the UI design is very modern, meaning it's just packed with dynamic elements. So he clicks this toggle menu button, a sleek sidebar slides in, and obviously the layout shifts.
Right, the available space shrinks.
Exactly, the space for his chart shrinks, but the chart itself just stubbornly maintains its original width, getting clipped behind the sidebar. It's like it doesn't even know the sidebar is there.
Which is incredibly frustrating for him. I mean, the math to render that canvas is entirely correct.
Right.
The proof is that if Timothy reaches up and, like, physically drags the edge of his browser window to make it narrower, the chart redraws and scales perfectly in real time.
Okay, let's unpack this. Why does the canvas scaling logic execute flawlessly for a physical browser window resize, but then it completely fails to fire when an internal DOM element, like a sidebar, alters the layout geometry?
Yeah, so that right there is a fundamental architectural divide between how the web used to work, back in the day, and how it operates today. The article highlights a senior developer named Margaret, who spots Timothy's issue instantly.
Hmm.
She sees that he is driving his Kansas redraw logic using a standard window event listener for the resize event.
Ah, okay.
And she correctly identifies that approach as, well, a blunt instrument.
A blunt instrument. I mean, that makes sense intuitively, but let's look at the actual mechanism here, because my first instinct as, say, a React developer wouldn't be to reach for a window event listener anyway.
Right, you'd think in terms of state.
Exactly. If I have a sidebar opening, I have some application state tracking whether that sidebar is open or closed, right? So wait, couldn't Timothy just tie the chart's redraw logic to the specific toggle menu button? Like, just pass a Boolean down saying, hey, sidebar opened, trigger a re-render? Why is the article suggesting we need some specialized browser API for this?
What's fascinating here is that relying on application state to manage localized DOM geometry is actually a massive architectural trap.
Oh, really?
Yeah, Margaret addresses this directly. She warns against building what she calls a tightly coupled nightmare.
A tightly coupled nightmare. Okay, let me guess. If he ties the chart's redraw logic to that specific sidebar state, what happens when the design team decides to add like a collapsible notification banner at the top of the screen next week?
Exactly. You'd have to wire the chart to listen to that banner state too.
Oh, man.
And it gets worse. What if a separate component, let's say a data table right below the chart, dynamically loads more rows from an API and pushes a scroll bar into the viewport?
Oh, right. Because the vertical scroll bar takes up, what, maybe 15 pixels of horizontal space?
Yes. The sudden appearance of that scroll bar changes the horizontal width of the container. So is Timothy supposed to track the data loading state of entirely unrelated sibling components just in case they trigger a layout shift?
Wow, yeah, I see where this completely breaks down. He'd essentially be forced to create this massive tangled web of global state where every single component has to broadcast its structural changes to everything else on the page.
Which is awful for performance maintainability.
Right, you're no longer just managing UI state. You're basically manually managing a global layout engine in JavaScript, which sounds incredibly fragile.
It totally violates the core principle of component isolation. I mean, if you have to pass props across 5 different components just to tell a canvas it has fewer pixels to work with, your architecture is hopelessly tangled.
Yeah, every new feature becomes a risk.
Exactly. Anytime a developer adds something anywhere on the page, they risk breaking the chart because they didn't know they had to manually alert it to a dimension change.
Which I guess brings us back to why he fell back on the window resize method to begin with. He just wanted a single unified signal that the available space had changed.
Right, the old faithful window resize.
But in a modern application, built with CSS Grid or Flexbox, layout geometry is constantly shifting without the viewport itself moving a single pixel. So the window object doesn't care that your Flex container squished your chart.
It doesn't care at all. The global window object is entirely blind to internal CSS layout shifts. So Timothy's chart is just sitting there waiting for a global event that simply isn't going to fire when that sidebar slides over.
Margaret gives a brilliant analogy in the source text to visualize this inefficiency.
I love this analogy.
Yeah, she says, using the window resize event to watch a specific component on your screen is like waiting for a citywide blackout siren just to find out your toaster finished.
It's so good. It perfectly captures the scale of the mismatch there.
It really does. I mean, it's like the difference between long polling an entire database every 5 seconds to see if one record changed versus just setting up a targeted webhook.
Exactly.
You're waiting for this massive, global, almost catastrophic event, the entire browser window resizing just to check on the localized state of a tiny wrapper div.
And that mismatch is exactly why Margaret introduces the hero of the article, the Resize Observer API. She notes that developers might already be familiar with this pattern if they've used the intersection observer, to track when an element scrolls into view.
Oh, yeah, for like lazy loading images and stuff.
The Resize Observer just applies that same targeted philosophy, but to an element's dimensions instead of its position in the viewport.
Here's where it gets really interesting, though. Because the article touches on the fact that this isn't just a syntax improvement. It's a fundamental shift in how the browser handles the computational load.
Huge shift.
By utilizing Resize Observer, we are essentially handing the heavy spatial mathematics over to the browser's highly optimized internal C++ engine. So how much overhead are we actually saving on the main JavaScript thread here?
An enormous amount. And to understand why, we kind of have to talk about how the browser renders a page. Historically, if you wanted to know the exact dimensions of a DOM element after a layout change, your JavaScript would have to call a method like getBoundingClientRect.
Which is notoriously expensive.
Highly expensive. When your JavaScript asks the browser for the exact pixel dimensions of an element, you are often triggering what is known as forced synchronous layout, or layout thrashing.
Okay, let's break down the mechanics of layout thrashing for the listener real quick. The browser has a specific render pipeline, right?
Right.
It parses the HTML, calculates the CSS styles, determines the layout, meaning the actual geometry of the boxes, and then finally paints those pixels to the screen.
Yes, the render pipeline. And usually, the browser is very smart about this. It likes to batch all the layout changes together and do the math once before the next frame is painted.
Makes sense.
But when your JavaScript single thread suddenly pauses and says, wait, give me the exact width of this wrapper div right now, the browser basically panics.
Because it hasn't finished the batch yet.
Exactly.
Yeah.
It has to stop what it's doing, immediately run all the complex layout math for the entire page to ensure it's giving you the correct number, and then return it to your script.
So if you have a window resize listener that fires, say, dozens of times a second as the user drags the window.
Which they do.
Yeah. And inside that listener, you are calculating DOM measurements. You are essentially forcing the browser to recalculate the entire page layout synchronously over and over again. You're just blocking the main thread entirely.
Which is exactly why older web applications used to stutter and lag so badly when you resize them. It was horrible.
Right.
But the Resize Observer bypasses that bottleneck entirely. You aren't asking JavaScript to calculate anything. You are configuring a passive sensor natively within the browser engine.
You're pointing the browser's native C++ code at a specific DOM element and saying, hey, you handle the layout pipeline exactly how you want to at your own optimized speed. Just let me know when this specific element's layout rect actually changes.
Yes. You're delegating the surveillance to the layer of the browser that is already doing the geometry calculations anyway.
That is so efficient.
It is. The Resize Observer specifically hooks into the browser's lifecycle to batch those measurement notifications before the paid cycle and then delivers them to your JavaScript asynchronously. It completely eliminates layout thrashing.
Going back to the analogies, instead of listening for the citywide blackout siren, you're wiring a smoke detector directly into the kitchen. The kitchen being, the specific wrapper div that contains Timothy's canvas chart.
It's an incredibly elegant architecture. You just instantiate the Resize Observer, hand it a callback function containing your canvas redraw logic, and then tell it to observe the specific DOM node holding the chart.
And this establishes what the article refers to as self-aware components.
Which is really the holy grail of modern UI architecture.
It really is. A self-aware component means the chart completely manages its own spatial relationship. It doesn't care that the user triggered an application state change, like opening a menu.
Right.
It doesn't care that a CSS animation is currently running. All it knows is that its immediate physical boundary has shifted.
The specific cause of the layout shift is decoupled entirely from the reaction to the layout shift.
And looking at modern frameworks, the developer experience for this has become incredibly streamlined.
Oh, absolutely.
Like, if you're working in an ecosystem like React, you don't even need to manually set up the observer instantiation in most cases. You just pull in a hook from a library, like use Resize observer, pass the reference to your div, and it handles all the raw API setup for you.
Yeah, returning the current dimensions as variables you can immediately use in your render cycle.
Right. It abstracts all the boilerplate away so you can focus entirely on the behavior of the component. You just drop the hook into your file, and instantly that piece of the UI becomes structurally independent.
It's almost zero friction for the developer.
So what does this all mean? I mean, it sounds like magic. Drop in a localized sensor and let C++ handle the complex math. But there has to be a catch. Are there any hidden traps for the developers listening when they switch from global event listeners to these localized observers?
If we connect this to the bigger picture of application performance and memory management, there is a very critical warning embedded in Margaret's advice.
Okay, lay it on us.
The power of decoupling your components comes with a strict responsibility regarding garbage collection. She tells Timothy he must ensure he explicitly calls the disconnect method on the observer when his chart is no longer needed.
Right. Like if the user navigates from the analytics dashboard over to their user profile page, that chart component is removed from the DOM.
Exactly. When you create a resize observer, you are essentially creating a strong reference binding between the browser's internal engine and that specific DOM element.
Right, they're tied together.
And the JavaScript engine's garbage collector, its job is to look for objects in memory that are no longer reachable by the application so it can delete them and free up RAM.
But if you navigate away and destroy the chart and you forget to tell the observer to stop watching?
The observer still holds a reference to that destroyed DOM node.
Wow. So the garbage collector looks at that detached DOM tree, sees the observer's reference, and basically says, oh, the browser is still actively watching this. Better keep it in memory.
Precisely. So the browser engine is just perpetually watching a ghost element that isn't even on the screen anymore.
That is wild. And if the user is navigating back and forth in a single-page application, continuously creating and destroying those chart components over a long session.
You are stacking up detached DOM trees in the background over and over. That is a textbook memory leak.
Ooh.
The application will slowly consume more and more of the user's RAM until the UI becomes super sluggish, or worse, the browser tab outright crashes.
That is a crucial caveat. You really have to clean up after yourself. I mean, if you're using React hooks like we mentioned earlier, the book usually handles the disconnect in its cleanup function automatically.
Right, the libraries usually protect you there.
But if you are writing vanilla JavaScript or setting up the class yourself, failing to unobserve that element is going to silently tank your application's performance.
It just highlights that while modern APIs give us incredible tools to solve complex architectural problems, they still require a solid understanding of how the browser's life cycle actually operates beneath the surface.
Very true. Well, let's bring this all back to Timothy's desk for the payoff. Because seeing this pattern resolve the bug is incredibly satisfying.
It really is.
So he deletes the global window event listener from his file. He abandons the whole idea of passing complex state props down from the sidebar. Instead, he instantiates the resize observer and points it squarely at the chart's container div.
And then, to test it, he leaves his mouse completely off the edge of the browser window.
Yeah.
The viewport remains totally static.
He clicks the toggle menu button. The application state updates, the CSS kicks in, and the sidebar slides smoothly into view. The main Flex container on the page is naturally squeezed to make room.
And the moment that container's geometry changes, the browser's C++ rendering engine detects the shift natively.
No JavaScript blocking.
None. It batches the measurement, entirely bypassing any layout thrashing, and asynchronously fires the observer's callback.
Timothy's JavaScript is essentially tapped on the shoulder with the exact new dimensions. The canvas recalculates its internal scale, and it redraws flawlessly.
Perfect synchronization.
Yeah, it shrinks in perfect sync with the sliding sidebar, never bleeding over the edge, never freezing up the main thread.
Because it operates completely decoupled from the rest of the application. It relies on a highly performant, localized sensor rather than a blunt global instrument.
The chart finally knows exactly when its own world changes. And I think this really encapsulates the core takeaway of our deep dive today. If you are building UI in the modern web relying on global window resizes or tangled application state to manage component-level geometry, well, it's an anti-pattern. We need to stop waiting for the city-wide siren.
Exactly. The objective is to architect systems where components are self-aware. Elements should manage their own spatial boundaries and adapt to their localized environments, trusting the browser's native APIs to do the heavy mathematical lifting efficiently.
It really changes the entire philosophy of how you structure a page. Which leaves me with a final provocative thought for you to ponder as you look at your own code bases. We've spent this time discussing how we can equip individual web components with their own independent, localized sensory inputs, right? We are giving them the ability to monitor their own spatial environments entirely independent of the main browser window.
We are shifting the responsibility from global awareness down to hyperlocal awareness.
Exactly. So does this mean the traditional concept of a top-down master page layout is becoming fundamentally obsolete?
Oh, that's an interesting way to look at it.
If every chart, every navigation menu, and every data card can independently self-regulate, calculate its own layout, and adapt based solely on the immediate container it's dropped into, are we moving toward a web where elements behave much more like decentralized living organisms reacting to their microenvironments rather than static blocks being orchestrated by a master page script?
It certainly feels like the architecture is evolving in that direction.
It really makes you rethink what a web page actually is at its core. Next time you click a menu and that chart seamlessly resizes without bleeding over the edge, you'll know exactly the kind of highly performant, localized magic happening just beneath the surface.